Now, in this particular package, we are going to look at the application of differential equation. You see, differential equation is applied to real life. It is not something that we just learn abstracts. It's applied to real life. So let's see how we can apply it to real life. Differential equation can be applied to real life, to solving, let's put that, to solving real life problems. In the area of sciences such as biological science, social science, and in the area of technology, such as engineering, etc. Now, these are the areas, and no, in fact, the differential equation, like I've told you, is something we use and solve real life problems. And what it entails is for you to observe the real life problem that you want to solve, and then you can now use mathematical equation, that is, you use variables to represent a particular observation, and then you now use it and solve the problem that you want to solve. By the time we look at it, you see that it is really giving solution to real life problems. Now we look at area like, look at growth and decay. Look at area like growth and decay. We'll look at Newton's law of cooling. We'll also look at area like electrical circuits. We'll also look at area like mechanics. So I think these are the 4 areas we will look at now. So we'll pick example about growth and decay, and we see such problems that we can use differential equation to solve involving growth and decay. So we want to look at example that concerns growth and decay. So a culture initially has 100 bacteria and 160 bacteria after 20 hours. If the rate of growth is proportional to the number of bacteria present, how many bacteria will be present in the culture after 100 hours? So you see, this is a problem we can use differential equation and solve it, and also predict the number of bacteria that will be in that culture in the next 100 hours. Now see how it works. we take the solution. Now we let x be the number of bacteria at any time t. Then, according to what the problem states, that if the rate of growth is proportional to the number, look at that. There is keyword there. It's proportional to the number. The rate of growth, that is the rate of change from the present condition to another condition. That's the rate of increase has occurred, and which of course we know that corresponds to the rate of change when we talk about differential coefficients. So we now see, since x represents the number, therefore the x all over the t, that is the rate of increase with time, is proportional to x. The rate of change, the rate of increase is proportional to the number. Look at to the number, because the number was x, so the x, the t is proportional to x. And we know that if we have this sort of differential equation, for us to change this proportionality sign, we have to write that the x all over the t will be equal kx. And look at that, is equal kx. And we see a differential equation that involves separation of variable, which we have known. Okay, so by separation of variable techniques, then we will have that the x all over x will be equal k dt. So we have separated the variable now. Right. Now integrating both sides, we'll have ln x will be equal kt, yes, plus c. Now if we have that, we can take log, ln, take ln of both sides. If we do that, we will have that x is equal exponential kt plus c. Of course, we should know that this is the same thing as x is equal exponential kt times exponential c. According to law of indices, if I write like this, then since the bases are equal, I can take one of the bases and add the powers. So I'm trying to separate this one so that it will be clear. Which means that x can be written as a exponential kt. Now this is, let me call this equation 1. We are going to really work on equation 1. So it's worthy to note equation 1 that most of the problem we are going to solve here will making reference to equation 1. Now don't forget also that a is equal exponential c. That's what is a. I'm representing a in the place of this. So that at t is equal 0, that is the start. We have been able to derive this equation now. So at t is equal 0, which is the start of observation, we have that x, according to the question, see, a culture initially has 100 bacteria. That is at the start. T is equal 0. The number was 100. So what we do now, from 1, we write 100 will be equal a exponential k 0. You know, t is 0. So, and we know that 0 times k is 0. And we have exponential 0. So anything raised to 0 is 1. So that means a is 1. I mean a is 100. So it implies that a is equal 100. Now, another one is that the number was 160 after 20 hours. That is at t is equal 20. The number was 160. So we now look at it and say at t is equal 20, x is equal 160. So you can put these values in equation 1. In equation 1, I've told you that we will be making use of equation 1. So we have to put it in equation 1. And when we do that, we have that 160 is equal a, and a is 100 that we have seen, and then exponential kt. Of course, t here is 20, which means we have 160 is equal 100 exponential 20k. So that exponential 20k will be equal 160 divided by 100. Of course, you know that this 0 can cancel 0. So what we have there is 16 divided by 10, which can be 8. Yeah, 2 can go here, 2 can go here. Can give us 8 over 5. Now, exponential k is equal, exponential 20k is equal 8 all over 5. So the next thing we'll do is to take lane of both sides. And if we do that, of course, we know we'll have 20k because this is exponential. So we have 20k will be equal lane of 8 over 5. So lane 8 over 5, lane 8 over 5 will have, you see, if the next thing is 8 divided by 5. Okay, it's 1.6. So we have lane 1.6. Look at that. It's giving us 0.4700. Yes. So that k will be equal, you see, we'll divide 20 by k. So we have 1 all over 20 lane 0.4700. And that is k. Now, what it means is that we can, you see, lane of, already we have taken this lane, as lane of 1.6 will be equal this, sorry, lane 1.6, that is what it means, lane of this. Because 8 over 5 is 1.6, so lane of this is giving us this. And what we'll do now is to find k, which is this value divided by 20. And if we do that, we have that k is equal 0.0235. So that is k. And then when we finish with that, you see, the equation is not yet true. This is k. So the last part of the question was how many bacteria will be present in the culture after 100 hours. So that is the last part. So now what they want is at T is equal 100. What will be X? So we'll go back to equation 1. I've told you that equation 1 is very, very useful. This equation, very, very useful. Maybe you derive it. It helps in solving the problem. So we'll go back here so that we can find X. Now that we have A, we have K, we have T, so we can find X easily. So we now see, so X is equal 100, that is 100 for the value of A, for the value of A, 100 exponential K, KT. So T here is 100, so we say 100 times 0.0235. And you see, if we do that, you see that 100 times 0.0235 is giving us 2.35. So what we have is that X is equal 100 exponential 2.35. Of course, exponential 2.35 is giving us 10.485. So X will be 100 times 10.486. So like we approximate to 6 because it's 4.855. Now it means that X is equal, this times 100 can give us 1048. So that is the number of bacteria in the next 100 hours. It's very simple. It's very simple to follow. So we'll pick another example. So we'll look at another example which also concerns growth and decay. Now, in a certain culture of bacteria, the rate of increase is proportional to the number present. If the number doubles in 4 hours, number 1, obtain an expression for the number present in terms of T. Number 2, how many are there after 12 hours? Number 3, if there are 10,000 bacteria at the end of 12 hours, how many were present at the beginning? So you see, this problem we can use differential to solve it. Differential equation to solve it. Very simple. So as usual, let X represent the number of bacteria at any time T, so that the X all over the T is proportional to that, proportional to the number, so it's proportional to X, which we know that removing proportionality sign will attract a constant K. So by separation of variables, we can write X, the X all over X is equal KT. Then integrating, we integrate both sides. We have ln X will be equal KT plus C. So taking lane on both sides of both sides, we have that x will be equal exponential KT plus C, which we know we can write as exponential KT, or let's write A exponential KT. You see, this is the one we normally note, and this is the equation that they say we should derive. Recall that A is the same as exponential raised to C. You know, like I told you the other example, this thing I can write it as exponential raised to C. So if I do that by law of indices, I can also act like this. So that's why I write it in this form. Now, this answers question 1. We're able to obtain an expression for the number present at any time t. Then we'll now go to question 2. How many are there? That was the question. How many are there in 12 hours? But before we answer that, we must find the constant A, the value of this constant. So we can write it that, you know, the question was that at look at this, if the number doubles in 4 hours, that is at t is equal 4, the number is double. Remember, the number is x that we use to represent the number. So now see that at t is equal 4, the number which is x, and then is it x double. So what it means is that x is equal to x. X is 2 times x. At the same time, what happens is that this is the same, because if you compare it there, you see that x is equal a. So we can have 2a. That is what it means. So that because, you know, at t is equal 0, if I really want to find a separately, look at, if I put t is equal 0 here, now at t is equal 4, we are told that at t is equal 4, that x is double, so we have 2x. Now since x is equal a, that means at t is equal 4, we have that x is equal to a. So we now have that 2a is equal a exponential k times 4. Look at that. Which means you see, what we have here is that exponential 4k is equal to a all over a. Of course, this can cancel this, so we have 2. Now, if we take lane of both sides, we will have that 4k is equal lane 2, so that k will be equal 1 all over 4 lane 2. You see that? So 1 over 4 lane 2. Now we'll find the value of lane 2, and that gives us 0.693 divided by 4. So if you divide that by 4, 0.693 1 by 4, we have 0.1733. by approximation. That is K. So now, having got K, we have to go and answer this question. Talk about how many are there after 12 hours. That is at T is equal to 12. Then what we need is X. What will be the number? So what it means is that X, if we go to 1 again, X will be equal, 1 says that X is equal A exponential kt. But let me start from K and put the value of K and T. Then we'll have that A exponential K, and K is 0.1733 times 12. That will give us that X is equal, and let's see, exponential, see, we start from 0.1733 times 12. Yeah, it's giving us, so we'll have exponential 2.07, exponential 2.07, all right, will give us, we'll have X is equal A 7.9 A, which I can write as X is equal to, if you approximate this, we have 8A. So at the end of 12 hours, so X is equal 8A. But there is a question, the last one. Last one says, if there are 10,000, look at that, 10,000 bacteria at the end of 12 hours, you see, at the end of the 12 hours. So this is the end of the 12 hours. So if there are 10,000 bacteria, we will have 10,000 is equal 8A. That's what it means. There are 10,000 at the end. Then the question is, what is the initial? Look at how many were present at the beginning. So what we do now, we first of all find this value of A by saying that A will be equal 10,000 divided by 8, and then that will give us 10,000 divided by 8. We have 1,250. That is A. So we want to now see how many of the bacteria were there at the beginning. That is, at T is equal 0. You see, we will go back to equation 1. Equation 1 is very, very useful. At T is equal 0, we have that X is equal A exponential kt. So that X at T is equal 0, we have that, you see, A is 1,250, and then we also have exponential K times T. Of course, it will be 0. It will be 0. So definitely what it means is that X is equal 1,250. That is what was there at the beginning of the observation. So that is how we solve it. That's how we solve it. So another application that we are going to take is Newton's law of cooling. This states that the rate of loss of temperature of a cooling body is proportional to the difference between the body's temperature and the temperature of the surrounding So now, if we let theta denotes the temperature, that is the temperature of the body, yes, temperature, and that theta of T is the temperature of the body at any time T, and then we also let lambda or any other value that we can assign. Let's assign lambda to denote the temperature of the surrounding. So that lambda of T will be temperature of the surrounding at any time T. Then mathematically the statement, this law that we are stating could be written as the theta dt is proportional to theta of T minus lambda of T. That is what it means. So that by the time we remove the proportionality sign, we know that we have that the theta of T is equal minus k theta of T minus lambda of T. You know that because of the difference, this is what the minus above because of the difference. You see, we said that the temperature, the law states that the temperature of the cooling body is proportional to the difference between the body's temperature and the temperature of the surrounding. Alright, so now we are going to use it. This particular one is what we can use to solve any problems related to Newton's law of cooling. We'll look at example so that we see how it is applied. So let's look at this example. A body with an initial temperature of 160 degrees Celsius is in a room of constant temperature constant temperature of 30 degrees Celsius. If the temperature of the body falls to 140 degrees after 20 minutes, derive an expression for the temperature at any time t. What is the temperature after 60 minutes? Alright. Now, the number 3 is when will the temperature fall to 35 degrees Celsius? So let's look at the solution. First, we'll let theta be the body's temperature. Now that means the T is proportional to theta minus lambda T. This one is temperature of the surrounding. Now this is what we have already derived, and we can now write it as theta dt is equal minus k theta minus lambda of t. Okay, the question now is that a body with initial temperature of 160 degrees. So in a room of constant temperature 30. So what it means there is that, you see, like here, definitely, if we look at it by separation of variables, we can do something here about this. We can do something. So if I separate variable here, what I will really have is that the theta all over theta minus lambda of t will be the same as minus k dt. So we see that at this point, by integration, definitely what I have is ln theta minus lambda of t, which is equal, look at this, minus kt plus c. So taking ln of both sides, I will have that theta minus lambda of t is exponential minus kt plus c. But it is given that at t is equal 0 as initial temperature, means at t, that is an initial, t is equal 0. Then the temperature of the body is 160 at constant room temperature of 30. So that means 160 minus 30 is equal. Okay. Let's look at this. Let's look at this. That we can write. We can write this as. Look at this. Exponential minus kt times exponential c, where we have a exponential minus kt. Look at that. So that at this temperature 160, the room temperature is 30, and in the t is 0. So definitely what we have here is 160 minus 30, which is the room temperature, will be equal a exponential 0. When you have t is equal 0 times this, you have exponential 0, which is 1. Then this minus this will mean that a is equal 130 at this point. 160 minus 30. Alright. Now, another one is, after we have that, we have to also go to where we say, see another one, if the temperature of the body falls to 140 after 20 minutes. After 20 minutes. So we then have that 140 minus 30. Don't forget that 30 is the constant temperature. Okay. Minus 30 will be equal A. Of course, we have got the value of A. Let me just put it first so that you understand the flow. Exponential minus KT. And now this minus this will give us 9, okay, give us 110, that's 140 minus 30, will be equal, of course, A, let's put the value of A now, which is 130, then exponential, then T here is 20, so we have minus 20, minus 20K, 20 is 20, so minus 20K. Alright, which means that exponential minus 20K will be the same as 110 over 130. Of course, we have to divide this so that we get it 0.846. Alright, now if we take plane of both sides, so that we can get the value of K. So you see that we will have minus 20K will be equal to 0.846. Now, it means that K is the same as minus 1 all over 20 ln 0.846. That's good. Now, let's look at lane 0.846. 0.846 is giving us minus 0.1672, and if that minus times this, we'll have plus. So definitely, if we divide 0.1672 by 20, see what we have. We have that K is equal 0.008036. That is the value of K. Now, after having the value of K, he has not finished. We can now talk about what will be the temperature after 60 minutes. So that means at T is equal 60. See, that is what where we want to get the temperature now. Now let's go here. If we go to this place, we can get it from here. At T is equal 60. What will be the temperature? We'll have that theta minus 30 will be equal A, and A was already, we have it as 130, then exponential minus K, rather minus KT, so we have minus KT, K is 0.00836, and then T is 60. So if we times that, we will have, let's see what we have, 0.00836 times 60, giving us 0. So we have 130 exponential. Okay, this will be minus 0 because of this. So we have 0.00836 times 60 give us minus 0.5016. Now, if we take that to exponential minus 0.5016, we'll have 0.605, or let's call it 6 because of approximation. Okay, now if we time this by 130 times 0.606, we have 78.78. So theta minus 30 will be equal 78.78, which implies that theta, if we transfer this to this side, we can now say plus 30, it will give us 108.8 degrees Celsius. That is what we will have at the end of 60 minutes. So this is how we can solve it step by step to predict what we should have. Let's look at the last one as the number 3 of it. Is that when will the temperature fall to 35 degrees Celsius? So we'll now go back to solve for that. You see, T is the question. Now, when theta is 35 degrees Celsius, so what we are asked to find is the time that theta will fall to 35 degrees Celsius. You see, but we can take it from this equation, theta minus theta minus lambda of t. Remember, where we have that a exponential minus kt. The lambda of t is constant, which is 30. So when theta is 35, the constant temperature for the surrounding was 30. Of course, we have that our A here is 130, so let me just fix them one time. So that exponential minus k, minus k. K is, what do you get about k? 0.00836. So we have k is 0.00836 T. We don't have T. It's T that we are looking for. So we have that. You can then say that 35 minus 30 give us 5. But see what we will do to help us. Let's put it this way, so I will really get it right. Minus 0.00836 T. So we can get exponential minus 0.00836 T is equal, I'm making this subject of the formula first so that you understand. I'm making this subject of the formula so that I can divide 5 by 130. Okay, if I do that, I will have 0.0385 by approximation. Now, this is equal to this. That means taking length of both sides. So taking length, we have minus 0.00836 T will be equal 0.0385. So that T, of course, this is okay. Taking length of both sides, it will be length 0.0385, length 0.0385, and then length 0.0385 giving us minus 3.257. Okay, so minus 0.00836 t is equal to this, so that t will be minus 3.257 all over minus 0.00836. Of course, if I do that, 3.257 divided by 0.00836. Okay, that gives me 389.5 minutes, because we were calculating in minutes. So that is T. That is the time that the temperature will fall to 35 degrees Celsius. So this is how it is done. It's very simple to follow. And the next application we want to look at is application to electrical circuits. You see, if we want to solve problems of differential equation, for instance, to electrical circuit, there are basic things we must note, which I say we must know that in electrical circuits, for instance, let's look at electrical circuits that contain resistor R, and they also have inductor L. And this is where we have the electromotive force E. Now in these circuits, some electrical circuits will contain resistor, inductor, and capacitor. It can also contain resistor and inductor. But I'm taking the one that contains the resistor and inductor anyway. So the basic things that we have already known, which that the voltage drop across resistor, that is, notice that voltage drop across resistor in a closed circuit across resistance, or let's put it resistance R in a closed circuit is R times I. Of course, I is the current, So, voltage drop across inductance L is equal L di dt. In short, we really know that there's a special lecture for electrical circuits. We know about electrical circuits, so I'll just go straight to the application, not the derivation. Most of our lectures we like deriving how it started, but it is assumed that students, they know about electrical circuits, they know the resistor, they know the inductor, so we'll go straight. We don't have capacitor, but even though we have capacitor, we should also apply it, but it's not applied here. It's only these two that we are considering. Then after knowing this, what again we need to know is for the Kirchhoff law of voltage is very important. Kirchhoff law. What it said is that now this states that the algebraic sum of the voltage drop in a closed circuit is equal to the resultant electromotive force E. Electromotive force is represented by E. Alright, now that means what we have is that Ri times L di dt is equal to E. This is T, where we can write it like this: R L di all over dt plus Ri is equal E. It's another way to write it again is di dt plus R over L, I is equal E L. You see what I mean? I just divide through by L, and then we see a clear first order. Yes, we see a clear first order non-homogeneous equation. Now, having got this, next thing we look at is our integrating factor. You know that we normally use integrating factor to solve first order non-homogeneous equation. So integrating factor, like we have derived, is equal exponential integral. Look at that. Integral R, because this is what we will integrate. So R all over L dt, integrating with respect to t. Of course, that will give us exponential R over L t. Okay, so that is what it will give. Now we are going to multiply it through, and then we will have exponential R L t, R over L t di dt plus exponential R over L t R over L I will be equal exponential R over L t E all over L. You see, we are just multiplying all of them through. And if we do that, we know that this is the same as d dt of exponential R L t times I. This is the differentials of this. We know that one in first order. We have just finished first order. So you should know this. So it is assumed that you have watched our lectures on first order, which is a package in this lecture. So you have watched it so that you understand how this is done. Now, if we have this, it's the same as exponential R all over L t. Then we have E all over L. So integrating both sides, with respect to t, we then have exponential R over L t times I. If you integrate this, you get back the inner function. It will be equal to integral exponential R over L t E all over L dt, and that will give us. Now let me bring this out, this constant, bring it out. So we have exponential L, and we have integral exponential R L t dt. Look at that, dt. So that means we integrate here. Definitely we know we will have E all over L. Yes, E all over L. When we integrate this, we have R all over L all over exponential exponential R all over LT. That's what we have. Which if you times this, see what we have. By the time you times this 1, we'll get something like this. L all over E all over L times L all over R. That's what it means. Because this one is up here. So by the time you invert it, L will cancel this. Exponential R over L T. Which gives us this cancel this. We have E all over R exponential R all over L T plus C. So what it means is that exponential R over L T R is equal this. Then at T is equal 0. Now that is the initial time at T is equal 0. You see, if you put 0 here, you have exponential raised to 0, which is 1. So I, you see that when you times this, you have 1, you have I. Then here again, what happened is that, okay, at T is equal 0. I should also know that I is 0 anyway. No current at that place. So everything here becomes 0. Now, if here T is 0, look at, I will have only this. So what I have here is 0 is equal E all over R plus C. So that C will be minus E all over R. See, I'm transferring this. Then if that happens, can now go back again to put the value of C, which I know that exponential, I'm going back here. So exponential R L T I will be equal E all over R exponential R L T minus E is minus E because C is minus E all over R. So that I will be equal E all over R exponential RLT minus E all over R exponential minus R all over LT. You see, I'm dividing through by this. So dividing it through by this. So I just carry it up. That's why we have this minus sign in this place. But I want to use it and times here. You know, if I use this and times here, definitely what I will have here will be E all over R, because this one plus this will give me 0. Anything less than 0 is 1. Then I have here this times this will give me E all over R exponential, look at that, minus R over LT. So definitely what it means is that I will be equal as it is. I can just factor out something here. Common thing here. That common. So I will be equal E all over R, yes, minus, okay, bracket 1 minus exponential minus R all over LT. So this is the current. Current will be given by this in electrical circuit that contains resistor and inductor. So this is how we can use it. But let's look at example of it. It's very simple. It's very simple to follow when you know first order differential equation. Very simple to do. All right. So we look at this example. A coil having a resistance of 15 ohms and an inductance of 10 Henry is connected to 90 volts supply. Determine the value of current after 2 seconds. we are going to take exponential minus 3 to be 0.05. Now look at the solution. First, let's sketch the circuit. So you see that this is the flow, the current. So we have the resistance and inductance there. But we are given that electromotive force is 90 volts. That's what we are given. So what we should know is that voltage drop across the resistance R is equal R times I. The same thing happens for inductance L, which is equal L di dt. So that by Kirchhoff's law, we know that the algebraic sum of the voltage drop in a closed circuit is equal to the resultant's electromotive force. So if we put that in use, we have that L the I all over the T plus R the I will be equal E. Yeah, it will equal E. That is what this electromotive force. So if we add this and this is equal to electromotive force. That's what the law states. So which we can write as the I all over the T plus R over L. I is equal E all over L. You see how we follow the pattern that we used before to prove. So at this point, we are told that the resistance is 15 ohms, while the inductance is 10 Henry. Okay, so we have to have the electromotive force to be 90. That is, R is equal 15 ohms, L is 10 Henry, then E is equal 90 volts. So if we put that here, we have the I all over the T plus, look at R is 15, L is 10, I will be equal 90 over 10. And if we have that the I, the T plus, okay, let me simplify here to have 5 can enter here, okay, 5 can go here, 3 times, 5 can go here 2, so we have 9 when we divide it by this. Now we have to recognize the integrating factor which is given by this. We know that integrating factor will be equal exponential integral ax dx, and in this aspect our ax is 3 over 2, so this gives us exponential integral 3 over 2 dt, because this one is in terms of x, so we are doing in terms of t, so we have dt. Of course, this will give us exponential 3 over 2t. Now, the next stage is to multiply this equation, this particular one. Let me name it. Start this equation by exponential 3 over 3t. So if I do that, I will have exponential 3 over 2t, that's a times again, di dt plus exponential 3 over 2t I will be equal 9 exponential 3 over 2t. I've multiplied through. So this gives me ddt of exponential 3 over 2t times r, which is equal 9 exponential 3 over 2t. Now integrating both sides, we'll have exponential 3 over 2t. I will be equal integral, integrating this side. Okay, let me just write this right. Integral exponential 3 over 2t dt. Which means, if you're here, we know that if we integrate here, we have exponential 3 over 2t all over 3 over 2. Yes, that is what we have. And then, you see, by this, what it means is that we have 18 over 3. You know how? This is 9. 9 times this over 3 over 2. So we can use 2 to times up here to have 18 over 3. So we have exponential 3 over 2t. 3 over 2t. So that at this particular place we have 6. 18 divided by 3 is 6. 6 exponential 3 over 2t. That is exponential 3 over 2t I is equal this plus c. You have to remember constant of integration. Now, at t is equal 0, I is 0. So that what it means is that the whole here will be 0. When I is 0 and this is 0, so everything is 0. 0 is equal 6. Because if this is 0, then we have exponential raised to 0, which is 1. So plus c, which implies that c is minus 6. If I transfer here, we have minus 6. Now let me go back to this place so that I can find, we go back here so that we can now see to this place so that we can now find the current. So now that I want to put t, I have that exponential 3 over 2t I will be equal 6 exponential 3 over 2t plus, okay, this is minus because of c is minus now, minus 6, and that will give us that I is equal 6 exponential 3 over 2t minus 6, alright, exponential minus 3 over 2t. You know what? I just divide here. Just divide by this. Both sides by this. So what I do here is to take exponential 3 over 2 up. So give me minus. So then become, if I use this to times here, definitely I will have 6. Then if I use this to times here, I will have minus 6 exponential minus 3 all over 2t. Yes, that's what I have. Which the sign I can write as 6, 1 minus, look at that, 1 minus exponential minus 3 over 2t. So it's still the same. Then the question was, look at, you said, determine the value of current after 2 seconds. So we now see that here, we can now say at t is equal to, that is here, we'll have that I is equal 6, 1 minus exponential 3 over 2, minus 3 over 2, yes, times 2. Of course, we now have 6. 1 minus, this time this will be minus 6. So minus 6 divided by 2, we have exponential minus 3. Okay. That is where they gave us the condition that exponential minus 3 will be 0.05. So we now have that I is 6 times 1 minus 0.05, because that was the condition that they gave initially. This will give us, you see, 1. 1 minus 0.05. They give us 6 times 0.95. And that gives us that I is equal 5.7 amps. So we can approximate it to 6 anyway, but so that is the value. It's simple to go about. It's very simple. We want to look at the raw scan of functions, what we call raw scan. Okay, let U of x and v of x be two functions continuous in the interval x less than a and less than b. Then u of x, v of x. U of x, v of x, and u prime of x, v prime of x is called the Wronskian of the functions u of x and v of x. So this is how we define the Wronskian of functions. So the Wronskian of this function u of x and v of x is the determinants of u of x, v of x, and the derivative of v of x being here, the derivative of v of x. Of course, we know how to take determinants from our first course mathematics. We know how to take the determinants of a matrix. So it's just the same way that we are taking. But putting these two functions and the next one we take the derivative. So that is what we call the Wronskian. So let's look at an example how we can apply the Wronskian. So we are going to find the Wronskian of the functions. First function is exponential x and exponential 2x. 2x squared, x and 1. So this one is sine x and sine x. So for 1, we see that the Wronskian of exponential x and exponential 2x will be equal to the determinant of exponential x, exponential 2x, and the derivative of exponential x, which is this. So we have 2 exponential 2x. That is also the derivative of this. Now, we know that this will be using this to times this. That is by determinant form. This time we have 2 exponential 3x. No, this time this. Minus this way we will have exponential 3x. So we have 2 exponential 3x minus exponential 3x, which gives us exponential 3x. So that is the Wronskian of these two functions. Now for I, we have that the Wronskian of 2x squared, and we have x1 will be equal to the determinant of 2x squared, x and 1. So differentiating this we have 4x. Differentiate this we have 1. This is 0. If we differentiate this again we have 4. This is 0 and this is 0. You see that when it is 3 functions, so we have to get up to 3 by 3 determinants. And this gives us 2x squared, by determinant form. 0 minus 0 minus x Ignore here and here. This time this we have 0 minus 0. Then plus 1. Ignore here and here. So this time this gives us 0 minus 4. So the whole thing there is minus 4. So that becomes the Wronskian for the function. Now let's go for 3. Wronskian of sine x and sine x will give us sine x. Sine x, of course, this will be cos x if we differentiate sine x. Then we also have cos x. Now the determinant is this. This time this we will have sine x cos x minus sine x cos x. That gives us 0. So the Wronskian of this function now is 0. Now there is something we observe here. If you have two functions of the same, you see, if you have two functions and they are the same, so it is certain that the Wronskian will be 0. You know, what I'm saying is this: we'll be using this in our second order homogeneous equation. I will be using linearly independent and linearly dependent. So anytime we will have a solution to the differential equation of second order, when we have two solutions which resemble themselves, so they will be equal to 0 if you take the Wronskian. But let's look at test of dependence and independence before. We will now know how we will really apply it. So the next subtopic is test of dependence and independence of functions. Now, two solutions of an homogeneous equation of the form d square y all over x squared plus a of x divided x plus a of xy is equal to 0. If I have homogeneous equation of this form, so the two solutions, know that this equation will resolve it to be two solutions. After now, we are going to enter solution to second order differential equation. So you see how we bring out the two solutions. Okay, now these two solutions of an homogeneous equation of this form is said to be linearly independent if the Wronskian is not equal to 0. It is linearly dependent if the Wronskian is equal to 0. So when we take the Wronskian of two solutions of a differential equation, if it is equal to 0, then we say that those two functions are linearly dependent. But if it is not equal to 0, we say that they are not linearly dependent. That means they are linearly independent. Alright. Now let's take example so that we will see how it works. Now the example is determine whether or not the following functions are linearly independent. So for us to know whether they are linearly independent or linearly dependent, we have to use the Wronskian. Now, solution. First, we take the Wronskian, that is number 1. Then the Wronskian of exponential x, exponential 2x, and exponential 3x, which will give us the determinants, the 3 by 3 determinants anyway. So this is exponential x. Differentiating this, we have exponential 2x. Here is exponential 3x. So here is exponential x. So 4 exponential 2x. And this is 9 exponential 3x. It is assumed that the students are familiar with differentiation, and I know that before you watch this type of lecture, you have offered elementary calculus. You know about differentiation very well. So now we have exponential x. You also know about this determinant. This time this will give us 18 exponential 5x. You see, this time this minus 12 exponential 5x. Then you have minus exponential 2x. We know here and here. Then you have 9 exponential. Okay, this time this 9 exponential 4x. Okay, so this can times this. We have minus 3 exponential 4x plus. Then taking this one, we have exponential 3x. This we have 4 exponential 3x. Then this time this will give us 2 exponential 3x. So this will be equal to exponential x. Now this minus this is 6 exponential 5x minus exponential 2x. This minus this is 6 exponential 4x plus exponential 3x. This minus this is 2 exponential 3x. So we see that this can give us 6 exponential 6x. That is multiplying this. We have 6 exponential 6x minus 6 exponential 6x, which is this. So then here is plus 2 exponential 6x, that is multiplying this by this. Now we see that this and this can go, so what we have is 2 exponential 6x. That is the Wronskian function of that two functions. Now let's look at 2. 2 is the Wronskian of exponential 5x exponential 5x. Of course, that is equal to this determinant 5x exponential 5x. So if you differentiate this, you have 5 exponential 5x, and this will also give you 5 exponential 5x. Now this time this will give us 5 exponential 10x minus 5 exponential 10x. So that gives us 0. Now, according to our definition, we said that that the two solutions of an homogeneous equation of this form is said to be linearly independent if their Wronskian is not equal to 0. So that means in example 1, where we have 2 exponential 6x like that, it means that the two functions are linearly independent. But in example 2, look at the run scan is 0, so the two functions are linearly dependent. Now, what are we doing when we start second order homogeneous equation, solution to second order homogeneous equation? I'll be telling you when we get the solutions. I'll be telling you the two linearly dependent solution, or I will be saying the two linearly independent solution. Now, what that means is that those functions will be linearly dependent if you test their run scan. So that is how it works.